This is brought to you by the Alumni Association of PISJ-ES.
Hey guys, in this video we'll be talking about a derivation of one of the very important laws of chemistry, or let's say laws of science. We'll be talking about a derivation of Charles' law and the Boyle's law. Well, don't get confused with these if you don't know them, and we'll be talking about them in other videos. But the derivation that we are going to be talking about is known as the Gay-Lussac's law. Well, what does the law say? The law states that in a container of fixed volume, this means that the volume cannot change. The volume of the container cannot change. It cannot expand or it cannot contract depending on the pressure, but the volume is fixed. So in a container of fixed volume, temperature and pressure is directly related. This means, in other words, that pressure is directly proportional to the temperature of the container, keeping volume as constant. So always remember, in all of these laws, there has to be Charles' law, Boyle's law, and Gay-Lussac's law. There has to be one parameter that is kept as constant, because otherwise there will be two things that will be changing. So this is a requirement whenever you're using these three laws. You have to keep, or any law actually, you have to keep one variable as constant, one or two variables as constant, and then you change on the rest of them. So this is our law. Now, what does this mean? Let's see here. And why? Let's say this is our container, and we know, let's say we have air in this container and it's closed from the top, and it is a rigid container. By rigid I mean that the volume does not change. So let's say these are the air particles in this. So let's just say at this point they are at a pressure of 1 atmosphere, or 1.015 into 10 to the power 1.013 into 10 to the power 5 pascals. So at this point, this is their pressure. What happens when I introduce heat into this system? Well, you would say that probably the particles get heated up, the temperature of the air increases, obviously. Let's say the initial temperature of the air was 40 degrees Celsius, and let's say after 2 minutes I put in my thermometer here and I check the thermometer, and after let's say 2 minutes, the temperature that I get is 80 degrees Celsius. So first of all, I'd like to clear some concepts on temperature. What is temperature? Temperature, in its simplest term, is a measure of the kinetic energy of the particles. So when the temperature increases, what it's actually measuring, it's not measuring the heat given to it. That is a wrong concept. What it's measuring the kinetic energy of the particles. So if the temperature has increased, I can safely say that the kinetic energy of the particles increase. Particles increase. Well, what does this mean? I mean, how do you imagine this? That the kinetic energy of the particles increase. We know that the kinetic energy is given by half mv square. So let's just assume that the mass of the particle is constant and it's not changing throughout its journey here, throughout its motion. So this is our constant. This is not changing for any particle or for any time period. This is not changing. At T1, that's if the mass was 2 into 10 to the power minus 10 grams, then at T2 it was the same. As in at time 2 it was the same mass. So this is not changing. Why is the kinetic energy changing then? Because of this variable here. The kinetic energy changed at time 2. We know the kinetic energy changed because the temperature changed. And this change in temperature signifies that there was a change in kinetic energy. And why was this change in kinetic energy? Because of this variable here. Because of velocity. Because in this case, let's say this is the constant. This is not changing. So kinetic energy only depends on the velocity of the particles. So we can say that since the kinetic energy has increased, the velocity of the particles have increased. The velocity has increased for the particles. So the average velocity for the particles has increased. Let's say if the particles at let's say this was time 1 and the particles had an initial temperature of 40 degrees Celsius and this was time 2, and the temperature here was 80 degrees Celsius. So the kinetic energy, if let's say, I'm just assuming two values of kinetic energy. Let's say it was 1000 joules here, and here it was just a random value, 3000 joules. We know this because the temperature increased, and temperature is a measure of kinetic energy. So if there is an increase in temperature, that means there is an increase in kinetic energy. So this means that the average velocity, let's say the average velocity of the particle was 60 meters per second, just a random value. So here the average velocity of the particle could be, I'm not calculating, I'm just assuming a value, just giving you a figure, an idea of what is happening. The average value of velocity would be something like, let's say, 105 meters per second. So this is increased. This is the main reason of this entire topic, this velocity, this average velocity of a particle. Well, you would ask me, Adil, what happens when the average velocity increases? Hold on, I'll tell you. So we know about temperature. Let's talk a little about pressure. What is pressure? Pressure is defined as the force per unit area. The force exerted by a particle on the wall of the container. Let's say it's a fixed container, it's a rigid container, the volume doesn't change. So the pressure is a measure of the force that this particle would exert on the wall. Now let's say initially it had a velocity of 2 meters per second. What happens? This particle comes here and slowly he moves, this particle moves here, collides with this part, then slowly he moves here, collides with this path, this wall, slowly he moves here and collides with this wall. It is this collision with the wall of the container that is that the pressure measures. Actually, it's a measure of this collision. However, what happens when I increase the velocity? This is a fixed container again, and this is the particle here. But this time the velocity of the particle is, let's say, 100 meters per second of this particle. What happens now? This particle moves quickly here, then here, then here, then here, then here, then here, then here. It's total random motion, but he's just colliding with as much of wall as this particle could get. So if I say that in a time of 2 minutes I'm measuring the collisions, the frequency of collision, the number of times the molecule collides with the wall. Well, if the velocity 2 meters per second, if it's a slow particle, let's say he would collide about 20 times. But if it's a fast particle, this particle might collide about 1,000 times. And pressure is this measure. I mean, if this particle collides 20 times, this directly tells me that the pressure of this particle, of this container, is low, because the frequency of collision is low. Frequency of collision of the particles with the walls of the container. And if this particle collides 1,000 times, well, the pressure is relatively higher, because the frequency of collision is higher. So now I've told you two things about temperature and pressure. So now you can imagine, probably, if I give you a container here, a rigid container, and if I tell you that let's say the initial pressure P1 is 90 atmospheres, the initial temperature is, let's say, 25 degrees Celsius. These are the particles here inside this. Now just make up a story for yourself. What happens when I increase the temperature to 100 degrees Celsius and the volume is fixed? This does not change. This does not expand because of the pressure. It has to, stay constant. So if I increase this temperature, what happens? The average kinetic energy, what happens for the in the first time? The average kinetic energy increases. Because of this, the speed increases. Because of the speed of the particle, the frequency of collision increases. And because of this, the pressure increases. So you can see what is happening. I increase the temperature, the average kinetic energy increased. Because average kinetic energy was simply half mv square, where mass was constant, so an increase in this meant an increase in velocity. And because of if the velocity increased, now the particles are colliding more frequently. This particle is doing like this, here, here, in just the same time. And since the frequency of collision increased, that is, frequency of collision tells us about the pressure that has changed. So pressure increased, and this happens vice versa. Let's see. If here we have a particle, a container, and I have particles here. Now I am increasing the pressure. Pressure increase. I am, let's say, putting in this, assume it like this, that I am putting in more particles. These blue particles are the new particles. Alright, so I am increasing the pressure. So what happens? Now, initially there were less particles, so less frequent collision with the walls of the container. But now, since there are more particles, there are more chances of collision. So the chances of collisions increase because now there are more particles. Let's assume it like this. If there are like two cars on a road and they are moving at 100 meters per second, well, the chances of their collision is less compared to the situation where, let's say, there are 100 cars on a road moving at 100 meters per second. Well, the chances of collision increase because now there are so many of them. The probability of them colliding with the walls increase. So when you increase the pressure, as in you add in more particles inside, the chances of collision increase. Because of this, because of this, the velocity increases. Because now they are colliding more frequently. So when they collide more frequently, they gain in more energy and they move more quickly. Their velocity increases. Since their velocity increases, again, their kinetic energy increases, which makes sure that the temperature also increases. So if there is an increase in pressure, the frequency of collisions increase, because of which might increase because of the velocity increasing, and then it increases the kinetic energy, which increases the temperature. And so you can see that pressure, as you increase the pressure, there is an increase in temperature, and vice versa.